This is yttrium oxide. It's a rare earth element which has been bound with oxygen, from lasers to dental ceramics to fighter jets. And it's one of 7 rare earth elements which China this year has restricted the export of.
From toxic waste to strategic resource, America's rare earth revival. This is yttrium oxide. It is a crucial rare earth element, chemically bonded with oxygen, found in applications ranging from cutting-edge lasers and specialized dental ceramics to advanced fighter jets. Significantly, it is one of the 7 key rare earth elements whose export from China has been heavily restricted this year. Most people walk right past a polluted creek without giving it a second thought. Yet, in specific regions across the United States, scientists made an unexpected discovery within that seemingly lifeless, dirty water, a finding that promises to change everything. With excavation efforts underway, Ramaco is initiating the first new rare earth mine in the United States in over 70 years. Beneath the telltale orange stains and sharp sulfuric odor of polluted streams, they unearthed critical rare earth metals. Now, deep drilling operations are resuming for the first time in a decade, aiming to better understand the extent of these rare earths and essential critical minerals lying deep below. These are the very metals that power our electric vehicles, modern smartphones, and advanced military weapons systems. And China, the nation that currently dominates the world's rare earth supply, is certainly taking notice. This deposit is quite different from other rare earth mines because it's located in soft rock, says an executive. It's shallow, easily accessible, and the sheer volume of the reserve is enormous. We intend to sell this material to domestic customers, and that, in essence, will be our answer to China's market control. The shocking discovery inside U.S. rivers. If you had walked along Decker's Creek in northern West Virginia just a few years ago, the water would not have seemed like a place fit for swimming or fishing. Locals clearly recall long sections of the creek flowing a deep, harsh orange with the surrounding rocks stained red and brown, and a pungent metallic smell permeating the air. The primary purpose of this infrastructure is to treat the raw, polluted mine water, a worker explains. The water emerging directly from the mines into the creek is highly acidic. It needs its Baus text Chas pH Darna to be raised. People often referred to sections of the creek not as a stream, but as a cesspool. Fish populations had vanished and aquatic insects were sparse. That unsettling color, however, was the first indication that a powerful chemical process was underway beneath the surface. The pollution originated from abandoned coal mines scattered in the hills above. When mining companies carved tunnels into the rock and subsequently abandoned them, they left behind extensive tunnel walls and piles of broken stone containing a shiny mineral called pyrite. Pyrite is famously known as fool's gold because of its misleading appearance, yet it lacks significant value on its own. Over time, when rainwater and atmospheric oxygen interact with the pyrite, a slow chemical reaction begins. The mineral decomposes, creating a type of acid. This acid then dissolves the surrounding bedrock, leaching out various metals. The ultimate result is a rusty, highly acidic discharge known as acid mine drainage, AMD, which flows continuously from old mine openings straight into nearby creeks and rivers. AMD doesn't just make the water look unappealing, it renders the stream virtually uninhabitable for most life. Crucially, even long after the mines cease operation, the drainage can persist for decades as water continues to permeate the old tunnels and waste deposits. For years, AMD in the Appalachian region was regarded purely as an environmental scourge. It contaminated drinking water, corroded essential infrastructure like pipes, and significantly lowered property values along waterways that should have been community assets. The lime slurry is pumped through these channels and into the chemical injection manhole, where it's introduced into the AMD flow. and engineer details. It's a continuous process, like filling a glass, as the water infiltrates directly or via groundwater. When chemists and geologists began to analyze this same polluted water with greater scrutiny, they found something astonishing. The acid that was dissolving metals from the rock was pulling out more than just iron and aluminum. It was also extracting a collection of metals that are largely unknown to the public, but are absolutely vital to modern technology: the rare earth elements, REEs. When you combine what we call pyrite with water, you essentially generate sulfuric acid and iron, a scientist clarifies. REEs are a group of 17 chemically similar metals clustered together on the periodic table. They are essential components in powerful magnets used in electric vehicle motors and wind turbines, miniature speakers found in phones and earbuds, the sophisticated guidance systems within smart bombs and fighter jets. In an extensive study analyzing coal mine drainage throughout the Appalachian Basin, researchers determined that this polluted water and the solid materials that precipitate when it's treated can contain REE concentrations comparable to some commercially viable ore deposits. A team of scientists collaborating with the U.S. Geological Survey estimated that AMD outflows in this single basin carry approximately 1 million to several million pounds of rare earth elements and yttrium annually, depending on flow rates and drainage strength. They highlighted that this quantity could equate to anywhere from a tenth to nearly half of the total rare earth materials consumed by the United States in a typical year. The reason these strategic metals accumulate in polluted streams is directly related to their chemical behavior in different aquatic conditions. REEs tend to remain dissolved and mobile when the water is highly acidic. In contrast, in a normal, clear stream with a neutral Sataus text, pH, Sataurs, they are far more likely to stay chemically bonded within the rock or soil. In acid mine drainage, the extremely low pond text, Chan-Allers, and high concentrations of other dissolved metals make it easier for rare earths to be stripped away from the rock and transported with the water flow. When this water enters treatment ponds or wetlands and the tonor text, pH, is intentionally increased, those metals then solidify and settle out into the sediment at the bottom. We process this drainage, and our facility is one of hundreds across West Virginia where we are actively cleaning the water and returning it to the river, thereby restoring aquatic life, a local water group member states. Deckers Creek perfectly illustrates this process in action. The creek flows for just over 20 kilometers from the hills of Preston County down to the Monongahela River near Morgantown. One of the most severe discharge points is at a location known as Richard Mine, situated just upstream from Morgantown. At this spot, old flooded underground workings continuously leak a stream of foul, low text pH tolerant water into a small tributary. It looks like a normal mountain stream further up. The rocks seem typical, the water's clear. But when you come down to the area below the Richard Mine, it's a completely different scene, an observer notes. You can clearly see the results of the acidity and the high levels of iron and aluminum entering the creek. Before treatment, this constant flow deposited massive amounts of iron and other metals into Deckers Creek every minute, every day. Eventually, state and federal agencies, partnering with local groups, funded the construction of a major treatment plant at the site as part of a comprehensive program to mitigate abandoned mine issues. The facility, which became operational in the mid-2020s, now prevents thousands of pounds of acid and metals from entering Deckers Creek annually, contributing to the return of trout and other sensitive aquatic species. When scientists from the West Virginia University, WVU, Water Research Institute examined sites like the Richard Mine, they looked past the discoloration and smell and focused on something else. They collected samples of the sludge, the material that forms when the treatment system adds lime to the acidic water, allowing the metals to settle in a holding pond. They analyze this dense orange mud to precisely measure the quantity of rare earth metals present. The Institute estimates that dried sludge from some southern West Virginia sites can contain approximately 1.5 pounds of rare earths per ton of dry material. Sites in the northern part of the state can approach nearly 2 pounds per ton. These concentrations are comparable to, or even exceed, the grade of some hard rock rare earth mines operating overseas. Given that the United States currently sources nearly all of its rare earth supply from China and a few other foreign producers, primarily in the form of finished products, developing a domestic source linked to legacy coal mines represents a powerful strategic advantage waiting to be fully realized. What elevates this beyond a local West Virginia story is that the same chemical signature has been observed in other historic mining regions. Studies conducted in western states, including investigations into AMD near Idaho Springs, Colorado, confirm that water draining from old hard rock mines also carries elevated concentrations of REEs, which transition into solid material when the water is neutralized. In essence, polluted creeks and their associated treatment ponds across multiple states are quietly functioning as a vast, self-replenishing network of man-made ore bodies, so long as the mine water continues to flow. From toxic sludge to valuable metal powders, to fully appreciate the significance of this, it's helpful to quickly review the standard process for producing rare earth metals. Normally, rare earths are found in extremely low concentrations, a mining expert states. This material, however, is probably running at around a 25% grade, which is phenomenal. To anyone who has experience with rare earths, this is truly a thing of beauty. Traditional rare earth mining typically involves vast open pits or deep underground operations, extracting rock that contains only minimal amounts of the desired metals. The raw ore then undergoes crushing, is soaked in aggressive chemicals, and must pass through multiple complex stages to isolate each element. During this process, miners frequently encounter and must manage radioactive elements like thorium that are naturally co-located with REEs. These steps dramatically increase costs, generate massive amounts of waste, and often incite strong local opposition, which is a primary reason why so much of the mining and refining infrastructure shifted overseas. In stark contrast, the river systems affected by historical coal and metal mines have already completed the initial dissolution process naturally. The inherent chemistry within the abandoned tunnels has dissolved the metals and transported them into nearby streams in a liquid state. Furthermore, existing treatment plants, initially constructed solely for water quality restoration, already precipitate these metals from the water and concentrate them into sludge. For anyone seeking rare earths, this means the expensive early stages of digging, crushing, and preliminary separation have already occurred without any extra blasting or drilling. The feedstock is readily available as a wet, metal-rich mud that must be managed and contained regardless, simply to keep the local streams clean. Finding hidden metals in river sludge is one thing. Transforming those findings into a reliable source of high-purity material that manufacturers and defense contractors can use is quite another. That transition moves the story from basic stream chemistry into the realm of large-scale engineering, where the genuine work of converting waste into a new resource begins. How the U.S. turns toxic sludge into valuable metals in AEI's standard treatment plant, the mine water flows into large mixing tanks. Workers introduce a white powder called lime, calcium hydroxide, a common alkaline compound. All of this work we've been undertaking with acid mine drainage over the years has had one core objective: to clean up the watersheds and restore the creeks, explains a Friends of Deckers Creek representative. The metal recovery is an attending benefit. The lime infusion lowers the acidity, making the water less harsh. As the Anoban text pH tolerance rises, many of the dissolved metals solidify into tiny solid particles. These particles are denser than water, causing them to sink. All of the subwatersheds in the Decker Creek watershed, Canes Creek was the most heavily contaminated, a scientist notes. The water then moves into massive circular tanks called clarifiers, where the heavy particles settle to the bottom as sludge, and the cleaner water flows over the top and continues downstream. The WVU team, however, innovated beyond this traditional single-step process. They discovered that by implementing a two-step Papanjau text Pendalan process, they could separate the metals in a way that significantly improved rare earth collection efficiency. Step 1. They first raised the Iki Arafada text pH dollars to approximately 4.5. At this level, large quantities of iron and aluminum precipitate out of the water and settle into sludge, but most of the rare earth metals remain dissolved. Step 2. They then increase the Town text Medas $5 further, up to around 8.5. This is the point where the rare earths finally precipitate out, along with other valuable metals like zinc and cobalt. By partitioning the treatment into two distinct stages, they can generate a denser, heavier sludge that contains a far greater concentration of rare earth metals compared to the typical waste produced by older, single-stage mine treatment facilities. At the Richard Mine facility, this new methodology influenced the plant's entire design. To manage the ongoing acidity, the engineers separated the cleanup process into two distinct paths. The standard sludge from daily water treatment moves in one direction, while the rare earth-rich sludge moves in another. This valuable rare earth stream is managed with meticulous care. The plant pumps this concentrated mix into long white fabric tubes known as geotextile bags, which are laid out in a segregated area of the site. These bags function as enormous filters. Water gradually drains out through the fabric, leaving behind a thick, heavy mud. Laboratory tests show that once this mud dries, it can contain roughly 1% to 2% rare earth metals by weight. This represents a massive increase from the trace amounts initially suspended in the raw mine water. Simply put, the treatment plant converts a toxic orange soup into a significantly more valuable commodity, a compact, easy-to-ship pre-concentrate of rare earth metals. Being so close to WVU is an enormous asset because of the research that takes place there. And Friends of EHIM. Deckers Creek works very closely with Paul's Water Research Institute, a local group member comments. This pre-concentrate is then transported to the West Virginia University Rare Earth Extraction Facility in Morgantown, situated within the National Research Center for Coal and Energy. The U.S. Department of Energy provided funding for this pilot plant to determine if rare earths recovered from waste streams like AMD could be developed into a sustainable domestic source. The facility more closely resembles a small industrial plant than an academic building, featuring rows of tanks, pumps, steel platforms, and frames filled with mixing units that run around the clock. The first step for the engineers is to redissolve the metals back into a liquid, but under carefully controlled conditions. Workers mix the dried sludge from Richard Mine with a mild acid, typically a form of hydrochloric acid or similar reagent, inside heated tanks. The acid effectively strips the rare earths and other metals from the solid material and pulls them into the liquid, much like warm, soapy water dissolving grease from a pan. Once this step is complete, they have a potent liquid solution containing all the metals extracted from the sludge. Unfortunately, we currently lack a domestic supply of rare earth elements, so we import virtually all of our required rare earths from the People's Republic of China, a Department of Energy representative notes. This includes the rare earth elements we desperately need, as well as the iron, aluminum, and other metals we don't. The critical sorting phase happens next through a process called solvent extraction. While the name is technical, the underlying concept is simple. When oil and water are poured into the same container, they separate. In the pilot plant, one liquid is water-based and holds all the metals. The other is an oil-like solvent specifically tailored to selectively capture rare earth elements while rejecting most of the unwanted metals. The plant runs both liquids through a long series of mixing tanks and settling tanks. In each mixing tank, the workers vigorously agitate the two liquids, allowing the rare earths to transfer into the oil-like solvent. They then allow everything to settle until the liquids separate into two distinct layers again. This process is repeated multiple times. After many stages, the vast majority of the rare earth metals have migrated into the oil-based stream. Once the rare earths are securely held within that organic liquid, the plant performs one final chemical reversal. It washes the solvent with a clean acidic solution, which pulls the rare earths back out into a water solution. However, they are now dramatically purer than before. After the engineers evaporate the water and complete the final chemical steps, the residue is a powder known as rare earth oxide. These powders are the commodity purchased by manufacturers of magnets, batteries, and specialized alloys on the global. Market-taught early results from pilot systems like this one have already successfully produced small batches of mixed rare earth oxide powders with purity levels of approximately 98% by weight. This level of purity is sufficient to definitively prove that this method can yield commercially viable material, not merely laboratory curiosities. When WVU researchers analyzed AMD sludge samples across the coal regions, they found that some sites in southern West Virginia contained about 666 grams of REEs per metric ton of dried sludge. Northern West Virginia sites reached about 750 grams per metric ton. In practical terms, this is roughly 1.5 to 1.7 pounds of rare earth metals in every short ton of waste. While these numbers might seem modest, they align with or even surpass the quality of some hard rock ore bodies mined in open pits in other nations. In some instances, the proportion of heavy rare earths in these sludges is notably high. Treating this material is a complicated process, but one that's actively being tackled by the Department of Energy and local watershed groups, a researcher states. This focus is critical because heavy elements such as dysprosium and terbium are the very ones the world struggles most to supply. To make the economics clearer, the WVU team studied the Omega treatment site near Morgantown, which cleans AMD from a legacy coal mine. Using real-world market prices and actual metal concentration levels, they estimated that the recoverable rare earth content at this single site could be worth around $1 million over time if fully recovered and sold. Considering that there are hundreds of similar treatment systems across the region, many of which must operate for decades just to maintain stream safety, it is evident that this is far from a minor side project. The Richard Mine plant itself is substantial permanent infrastructure. The total cost for bringing electricity to the site, constructing the treatment building, setting the tanks, and installing the clarifiers has exceeded $9 million to date. Most of this funding originated from West Virginia's dedicated reclamation funds and federal infrastructure programs, as the original mine owner is long defunct and the state is responsible for the cleanup. This potential is now being explored at other streams where AMD has been treated for years. Facilities along Three Forks Creek and tributaries of the Tygart Valley River, initially built purely for water quality compliance, are now being investigated as possible future sources of rare earth feedstock. The concept is not confined to Appalachia. The same two-step chemistry pioneered by WVU is being applied to the Berkeley Pit in Butte, Montana, a massive toxic lake holding tens of billions of gallons of acidic water left over from copper mining operations. When one begins the process of converting polluted water into the metals required for electric cars, wind turbines, and modern weaponry, the endeavor transcends mere environmental cleanup. It enters a broader geopolitical competition for control over these essential materials. The next segment of this story leads directly into that international clash. Why China is concerned about America's new metal source. For many years, the United States operated under the assumption that rare earth metals would always be easily available on the global market. Consequently, it shut down most of its own rare earth mines and processing facilities, opting instead to import the finished materials from overseas. Between 2020 and 2023, approximately 70% of all rare earth compounds and metals utilized within the United States originated from China. China's influence is even more dominant when considering the entire supply chain, from raw material extraction to the final product. China extracts roughly 70% of the world's rare earth ore, refines nearly 90% of the chemicals required to process that ore, and manufactures over 90% of the finished magnets. These magnets are integral to crucial technologies: electric vehicle motors, wind turbines, fighter jets, radar systems, submarines, missile guidance units, and the machinery underpinning clean energy systems. When all factors are combined, a single nation holds a controlling interest over materials essential for keeping electric cars running, household electronics functional, and advanced weaponry operational. Washington realized far too late that a significant portion of its modern economic and military strength relies on metals that are neither mined nor refined domestically. The one major U.S. rare earth mine in California has historically shipped the majority of its concentrate overseas, frequently back to China, for processing. This means that if Beijing chooses to raise prices, reduce exports, or alter its regulations, U.S. companies immediately feel the economic impact. Beijing has already demonstrated its willingness to exploit this advantage. Following a sharp increase in U.S. tariffs on Chinese goods, China retaliated on April 4, 2025, by imposing new export controls on 7 critical rare earth categories. These controls included several medium and heavy elements such as samarium, gadolinium, terbium, dysprosium, and lutetium, alongside materials related to scandium and yttrium. Export controls mandate that companies obtain a special government license to ship those metals, or any products containing them, out of China. Officials retain the power to delay or deny these licenses at their discretion. Within months of the new regulations, Chinese exports of specific rare earth magnets reportedly plummeted by about 75% because companies could not secure the necessary paperwork. Automakers across Europe, India, Japan, and the United States reported immediate supply chain disruptions. Industry groups in Europe issued warnings that production lines for electric engines were on the verge of halting due to magnet shortages, pushing some factories into full crisis mode as orders accumulated with no components to fulfill them. Later that same year, China further tightened the restrictions. In October 2025, Beijing implemented even more stringent rules that extended beyond the metals themselves to encompass the underlying technology and knowledge. Companies now require governmental approval to export technology related to the mining, processing, recycling, or magnet production of rare earths. Chinese companies and citizens also face new limitations on assisting with the construction of rare earth facilities in other countries. Furthermore, China's industry ministry released provisional rules granting the government significantly enhanced control over who is permitted to mine or process rare earths domestically, all framed under the protection of national security. These actions carry immense weight due to the economic scale involved. In the year 2024 alone, China exported approximately 58,000 metric tons of rare earth magnets valued at nearly $2.9 billion. Germany purchased almost a fifth of that volume, and the United States also acquired a very substantial share. When a country with this level of market influence begins using export licenses as a tool in international disputes, every factory reliant on these magnets must take serious note. China claims it is acting to safeguard its own security and respond to external pressure. Chinese officials often cite U.S. restrictions on advanced microchips and chip-making equipment, asserting their right to defend their national interests in kind. However, many Western governments and policy analysts believe China is leveraging its rare earth dominance as a primary negotiating tool in a wider geopolitical and technological competition. In this view, the restrictions serve as a powerful reminder that China can impose severe difficulties on any nation dependent on its metals for building electric vehicles, wind turbines, phones, or military equipment. This is precisely where the story of the rivers converges with a much larger global narrative. The acid mine drainage projects in West Virginia, along with exploratory work at sites like the Berkeley Pit in Montana, are no longer isolated scientific endeavors. They have become fundamental components of a national strategic initiative. West Virginia University and the Department of Energy speak openly about transforming AMD from a persistent regional environmental challenge into a viable resource capable of supplying a portion of the rare earth metals required for U.S. national security. They envision polluted streams and abandoned mine pits as locations where the United States can finally establish a robust domestic rare earth source that no foreign government can impede. From China's perspective, these developments are a clear signal that its long-held market advantage may not endure indefinitely. Thanks for reading. Now, check out the videos popping up on screen for more unbelievable stories.